Okay, this problem asks for, it's a titration. We're adding strong acid to a salt of a weak base. So we have hydrolysis going on here. So let's start by writing out the equilibrium reaction. So this is the sodium nitrate, which is a salt, and the sodium is a spectator ion. We don't care about it. But the nitrite, NO2 minus, is the conjugate base of a weak acid. So if we take NO2 minus and show adding it to water, it will take an H away from the water and make HNO2 plus OH minus, and it reaches an equilibrium. We don't have to worry about the Ka or anything, Kb or anything of this, the equilibrium system. We just go and then say, okay, we're adding HCl to this. So you understand that there's a considerable amount of this, which is a base, and there's some of this, which is an acid. But they didn't talk about making a buffer, so this is not really a buffer. It only has a little bit of this. So what we can do is say, how much of this do we have? So that's where we find the millimoles. So if we do 20 milliliters times 0.35 molarity, we get 7 millimoles. So we have 7 millimoles of the conjugate base ion in solution. And because they didn't talk about this at all, we're going to assume that there's close to 0 millimoles of this. And then we're going to look at the neutralization. So that's where we're adding the strong acid of HCl. It could have been a strong base, although probably not, because it doesn't have a considerable amount of acid there. So if we take the H ion from the HCl and add it to the NO2 ion, we get HNO2. And again, let's find out how much HCl we're adding. So if we have 20 milliliters of H ions and it's 0.25 molarity, 20 times 0.25 is 5 millimoles. So we're adding 5 millimoles of the strong acid. So that means that this is going to go down by 5 millimoles. And as it reacts completely, this will go up by 5 millimoles. So if we write out our buffer equation, even though this is not really a buffer, it is, because as it's neutralizing, the conjugate base is going down and the weak acid is going up. So the concentration of the H ions equals the Ka times the acid over the base. Okay, so the H concentration will end up helping us get our pH. The Ka comes from the nitrate ion, but we know that that's a conjugate base. So we take it back to the weak acid of that, which would have been HNO2, and we would look that value up if it wasn't given to us. So it's 4.5 times 10 to the negative fourth. And then we set up this fraction, which is going to be our millimoles. So again, the acid is not the strong acid that we're adding. It's the acid that matches the conjugate base from the equilibrium before. And again, that starts off as 0 millimoles. And we're assuming we mostly have the conjugate base ion, which is 7 millimoles. And so as we add the strong acid, the NO2 goes down by 5 millimoles, so the base goes down 5 millimoles, and the acid goes up 5 millimoles. So this fraction, we get 5 over 2, so it's 5 halves of the Ka, and then we negative log that to get the pH, which would give us 2.95. Okay, here we go.